Good morning, students. I'm Dr. Shiva. So I'll be handling you about the degrees of freedom system for a dynamically loaded structure. So before going into the single degrees of freedom system, so you should understand what is degrees of freedom. Okay. So degrees of freedom represents the number of coordinates required to mark the position of a structure after the point of loading. So for example, if you take a pendulum, okay, pendulum is fixed at the top and a free hanging pendulum is there. Okay. So when I apply a displacement, when I'm going to apply a displacement, obviously the structure or the position of the pendulum will goes like this. To mark this new position, I need some coordinates. Say the pendulum is moving in the x-axis. Obviously, I need only the x coordinate to mark the position of the new new position of the structure. Okay. So this is for representing the new position of this particular pendulum. We need only one coordinate, that is along x-axis. I can give you another example. Say a simply supported beam loaded with a center point load. Okay. So in this case, because of this point load, obviously the beam is going to bend in the y-axis. Okay. So it is going to bend only in the y-axis. So to mark the more position of the structure, I need only y coordinate to represent the new position. Okay. I can give you another example. Say if you take a cantilever loaded with UDL, right? So in this case, obviously the cantilever is used to bend like this, and I need to define the new position using only the y coordinate. Okay? I need only one coordinate to represent the new position. Now we can take a small portal frame, okay? Portal frame which is loaded with a horizontal force. Okay? Because of this horizontal force, obviously the structure is going to sway, okay, with some value, okay, which I'm going to represent using only one x coordinate. Okay, so if we take all these examples, we can understand that we need only one coordinate to represent the new position of the structure. Okay, these are some examples of the single degree of freedom system. Here we need only one coordinate to represent the new position. Okay, so now we are going to see another concept, that is mathematical modeling of single degree of freedom system. So how to make the mathematical modeling for a single degree of freedom system, that we are going to see. Okay, so say I'm going to take this portal frame, right? So this portal frame I'm going to take. Here in dynamics, we'll be considering one concept, that is lumped mass concept, in which we'll be lumping all the columns together in a single line. Okay, and this weight of the floor is considered as a single mass, that is the lumped mass. Okay, so the mass of this floor is taken as m, and the bottom is fixed, and the columns are represented by a vertical member like this. So if you take a vertical member, obviously a parameter called stiffness will comes into play. Because of this load or mass, the member used to deform to some extent. Okay, so the stiffness is generally defined as the load per unit deflection, right? Load per unit deflection. So so load here you can take mass by some deflection. Okay, so if you take any vertical member supporting a mass, will be having some kind of stiffness, that is K. Okay, this is the mass, right? So when I'm going to apply the load in terms of mass, obviously we will have different types of forces we have to consider. So for example, so the same structure I can able to represent it like, let us take this. I'm going to have a mass m. okay, which is supported on a roller, okay, and the member is having some stiffness. Usually here we used to specify the spring symbol, okay, this K, right, and mass is there, okay. So here we'll be applying an initial displacement in one direction, okay. In one direction we are going to apply a initial displacement which is happening in one direction. So this is a model for single degree of freedom system, right? So same structure, I'm just making it like this. So the bottom is fixed, and this is the bottom which is fixed, and the vertical member will be having a stiffness. So that stiffness is mentioned here, and this mass, lumped mass, is represented like a rectangular member with M. And I'm giving a roller support in which the mass will be freely acting on this spring, okay, which is the column. Okay, this structure is represented just like this. Okay, so now what we are going to do is we are going to frame equation of motion for this single degree of freedom system, for which you need to draw the free body diagram. So if I draw the free body diagram for this mathematical model, say M, so we need to understand what are the forces which will be acting on this mass, right? So we all know Newton's second law of motion, in which there will be some inertia force which will be happening in the structure. That is mass into acceleration. We all know this F equal to ma, right? Newton's second law of motion. So if you take any body, moving body, if you stop that moving body, obviously some inertia force which will be acting in the opposite direction. Okay. So if you take, suppose if we are traveling in a bus, okay, we are sitting in a bus and we are traveling. If automatically the bus stops, what happens? We'll be having a jerk. Okay, we'll be moving to and fro because of the braking action. So that action is called the inertia force. The same thing, if I'm going to apply an initial displacement here, obviously there will be some force which will be acting in the opposite direction. Okay, if I'm applying a force in this direction, the inertia force will be acting in the opposite to the force which is applied direction. Okay, so here, if I'm taking this free body diagram, obviously I'll be having an inertia force that is represented as mx double dot. Okay, here we are considering x as the displacement. Okay, and if we differentiate the displacement, obviously what we are going to get is the velocity. Okay, so if I differentiate the velocity, I'll be getting the acceleration, right? So that's why I've given mx double dot, and this spring is there, right? That will causes a force, spring force, which is given by kx. Okay, so kx is the what do you call it? Kx is the force, spring force. Okay, so as we all know, stiffness is what? Force per unit deflection, right? Force per unit deflection. And if I need the force, I have to cross multiply. So F equal to Kx. Spring force is given by K into X. So that's why I given K into X, right? So here initial displacement is given in the X axis. So there is no external force. So we are having only this force. Now, if we resolve the forces, the X axis, obviously what we get? Mx double dot. So since it's the horizontal left side, you can take it as negative. Ax equal to 0, and I multiply throughout with negative sign, you'll be getting this equation. And this is the equation of motion for single degree of freedom system. Okay, so I hope you can have understood about the single degree of freedom system, the concept of single degree of freedom system, mathematical modeling for the single degree of freedom system, and corresponding free body diagram for the single degree of freedom system, and the equation of motion to get for the single degree of freedom system. Thank you, students. We'll see in the next video about different concepts. Thank you.